So copper is a group 1b. And you can tell because of the electron configuration. How many valence electrons does copper have? One valence electron. Does everybody see this? Valence electron, again, is defined as the outermost electron. So then the highest end, which would be 4. The 3 would be considered inner electrons. 3 is inside of 4. And this is filled, so this is pretty unreactive. So it should be +1. But what's the most common charge to copper? Is it +1 or +2? +2 is much more common. If it's +2, then what must have happened to one of the D's? If it's +2, we're at D9. If we're at D9, then we screwed up the filled subshell. And is that okay? And it turns out it is okay for certain structures of copper. The D9 is preferred because that would be the lowest energy configuration. We aren't going to get into it, but there's a reason for that. So copper is a little bit different. However, silver behaves nicely. There's only one charge for silver. What is it? +1. Well, here, you got the krypton 4d10 core, 5s1 valence. So this is +1. Gold. Gold doesn't behave as nicely as well, but gold is +1 and +3. Gold is. If we look at gold, we got the filled 4f subshell, 4f14, filled d subshell, and that leaves the valence. The valence is always going to have the highest end, so this is 6. So it has 1 valence electron. And it doesn't mean that these electrons can't be attacked like they were for copper, you know. But it's highly unlikely to attack the noble gas core electrons. It's highly. All right, so we can get some ideas about the charges and some of the chemical properties of these. We can get some idea of the sizes. In fact, I need to talk a little bit more about the size. And the size is going to have an impact on reactivity as well. So when we look at the size trends, how would you summarize this? Yeah, the smallest is going to be hydrogen. The smallest? No, well, the smallest is going to be helium. So smallest top right, biggest bottom left. So cesium or francium would be the biggest. In terms of reactivity, the metal want to lose electrons. These, the nonmetals, would like to gain electrons. And so that means that it's flipped size trend. So fluorine's very small. Yeah, very reactive, powerful oxidizer. Iodine's very big, not as powerful. It still wants electrons, but not as much as fluorine. Over here, it's a different thing. We're looking at losing electrons, not gaining electrons now. So size plays the opposite effect here. Like potassium, much more reactive than sodium or lithium. But that brings up something that might raise a flag, and that is, what is the most powerful reducer on the chart? Something I asked you to memorize. Lithium is the most powerful reducer, but according to size, lithium should be the worst of these metals here, right? It should be the worst. And in fact, when you look at lithium, was it reacting very violently here? When we look at the reaction of lithium and water, it's not nearly as violent as the reaction of sodium or potassium with water. It's a lot less violent. And so why is it the best reducing agent? Reducing agents want to lose electrons. Water is taking the electrons, so why is it not reacting as violently as sodium and potassium are? It's smaller, therefore it should be less reactive. It should be harder to oxidize. It should be harder to take an electron off of. And so lithium's smaller, which is fine. It should mean that it's less reactive. But when we look at the redox chart, when I look at the redox chart, this is the redox chart from Flynn. What's here? Lithium. In fact, lithium's more powerful than potassium. And so why is that? It doesn't seem to make sense based on quantum so far. Let's see. Let's see if it comes out. Okay, now it's working. Well, maybe
6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire and burns with a light flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
That's cesium. Shattered the glass. That's an angry metal. It really doesn't like his electrons. It really doesn't like water.
yeah, so you would expect, cesium and rubidium and francium would be the worst out of all of them down here because it's so huge. You lose an electron easily. But why is this here? If you look at lithium and potassium, it looks like we got it backwards. It looks like lithium should be less reactive than potassium. And so this is the strange thing about charts like this. The strange thing about charts like this is we look at the total, cumulative effect. So initially there's more of a punch in the reaction. So yes, potassium reacts more violently than lithium. But when we look at the overall energetics, lithium is slow, but overall it's going to release more energy. It's going to be more exothermic. And the reason is it's not because of the losing the electron, it's because of the product, how stable the product is. And it turns out that lithium ions are a heck of a lot more stable than potassium ions. We'll talk about ions in water later. And so, this is a slow burn here, but overall more energy is released. And this is more rapid, more violent, but less overall energy is released. And so this is the reason why the lithium's at the top. But lithium's not the most dangerous. Potassium is way more dangerous than lithium. And they didn't get potassium to explode, but you can see potassium explode quite easily. But potassium is very, well, actually even sodium, but and I had the video up, I lost the address here, but we can just take a look at potassium. Well, this is water and sodium. Then we'll compare it with water and potassium.
So here is a larger piece of potassium going in.
Oh, that's potassium.
Quite a bit larger than the other ones.
Oh, actually, this is not the one I wanted.
And here is
That's potassium, the larger piece of potassium.
Very satisfying reaction.
The sodium's not, well, it depends on how big the piece and how much heat's generated and how quick it happens.
Very satisfying. Very satisfying reaction.
All right, so that's some quantum mechanics and chemical properties. We divide things, based on their valence electron configuration into families here. And then we have a smooth transition from metals. These are the most metallic here to the least metallic over there. And so what characteristics do metals and non-metals have? So let's just take a look at the definition, defining characteristics here of metals. On the left side we have the metals, and those tend to lose electrons. On the right side we have the non-metals, those tend to gain electrons. And then this 1, 2, or 3 valence, ignore this second line here, confusing. Metals have something called ionization energy. Metals have low ionization energy. Ionization energy is the amount of energy it takes to remove an electron off the atom, whereas nonmetals have high ionization. It's much more difficult to remove the electron. So when we're looking at removing electrons, we see that big atoms are easier to remove electrons off of. Small atoms are more difficult, harder. And so let's take a look at ionization energies next here. Okay, ionization energy is removing an electron. Well, actually, a gaseous atom, but we aren't going to get into that too. So this is ionization here. We take a neutral sodium. This is going to have the neon core up to here and the 3s1 valence. The 3s1 valence is right for oxidizer to come and take it. So an oxidizer can pluck off that electron, leaving us with a neon core here. And this would be the electron configuration for the sodium ion. And the oxidizer would make off with the electron here. Sodium's ionization energy is fairly low because it's easy to oxidize. Species, the hardest species to oxidize, what would you guess? The hardest species to oxidize would be helium. Helium's going to have the highest. Helium has the highest ionization energy. That means it costs the most amount of energy to take an electron off. What species would have the lowest ionization energy? Francium. Francium's not shown here, but you can see the pattern. We go lithium to sodium, from sodium to potassium. So potassium's easier to oxidize. It's got a lower energy oxidation. And then potassium to rubidium. You saw how violently rubidium reacted. And then from rubidium to cesium, it's down here. So, and so these species are easy to oxidize. These species are hard to oxidize. When we think about it, it has to do with size. And so if we know the size trends, let's go back and take a look at the size trends quickly. In the size trends here, and I ask you to summarize the chart in size trends, but it goes like this. Like here, hydrogen to helium, which one is smaller? Helium. Why is helium smaller than hydrogen? It's got more stuff. Shouldn't it be bigger than helium? Because the electrical forces. Helium's got 2 protons versus 1 proton. 2 protons can pull the electrons tighter. And so 2 protons pulls the electrons tighter, making it smaller. But when we go to lithium, lithium has 3 protons. Why isn't lithium smaller yet?
Because the energy level.
Yeah, because we jump up. Now we're not in the 1, we're in the n equals 2 energy levels. N equals 2 orbitals are bigger. Right? So we have another shell of electrons here. And so that's why the size jumps up, even though the number of protons. But now we stay in the same energy level, we stay in the same shell, and what happens? If we stay in the same shell, then it gets smaller and smaller as the number of protons increases. And so this is, and so the size will shrink with the number of protons as long as we don't add another shell of electrons. Now, if we add another shell, each time we add another shell of electrons, the size is going to increase. So that's the trend. Now, ionization energies, which one's going to be the hardest to take an electron off of? You'd think fluorine, but it's not fluorine. It's going to be helium. Helium's the smallest. That means the electron's most tightly held, and that means the electron's most nearest the nucleus here. And the easiest out of this will be cesium. Cesium electron out here. And so this is the size trend that we see graphically here. This is just a different way to represent it. So the first shell, we have hydrogen and helium. Helium is smaller, therefore higher ionization energy. Then we got to jump to the next shell. In the second shell, we start off at lithium. And so the ionization energy drops way down for lithium because we got another shell of electrons. But when we're in this second shell here, as we go across the second shell, it becomes smaller and smaller until we get to neon. And then we've completed this shell. There are some blips here, nitrogen to oxygen, beryllium to boron. These blips we can understand based on the orbitals, but I'm not going to get into it. We just know the general trend. The general trend is the ionization energy increases as we go across. And then as we jump down, it decreases to the next shell. So this would be the third shell. Complete the third shell, and then down to the fourth shell. So that's the trends we see. Now that's the trends for first ionization, but not everything forms +1. So there's a second ionization, or stops at +1, I should say. Everything does form +1 or can form +1. We have second ionization, third ionization, fourth ionization, etc. So this is the trend in first ionization. The smallest is helium at the top right. The biggest is cesium or francium at the bottom left. Ionization energy is just going to follow the same trend as the size. So let's get some practice here. Beryllium, nitrogen, fluorine. Beryllium, nitrogen, fluorine are all in the second shell. And so we just look at the size, beryllium, nitrogen, fluorine, which one should be the biggest, which one should be the smallest. So what happens if we're in the second shell? Maybe we can. What happens with size in the second shell? Beryllium, 111, nitrogen, 74, fluorine, 72. So the biggest is beryllium, the smallest is fluorine. And so the hardest to ionize will be fluorine. And so that should have the highest, followed by nitrogen, followed by beryllium. Beryllium's a metal also. Metals should be easier to ionize than non-metals. So that's ionization energy. Go back to this. Some other characteristics, metals are going to have low ionization, they should be easy to ionize. Non-metals have high, they're going to be hard. In fact, non-metals want electrons, they don't want to lose any electrons, typically. Metals can form compounds with non-metals, but not with other metals. Non-metals can form compounds with both metals and with other non-metals. Metals have high electrical conductivity. Non-metals have poor electrical conductivity except for graphite. Metals have high thermal conductivity. Non-metals have poor thermal conductivity. Metals are malleable and ductile. Non-metals aren't. Malleable just means hammered into different shapes and sheets. Ductile means dry and wired. It's just some basic properties. Okay, some of these electron configurations are quite complex, and then thinking about valence electrons can also get complicated. And so what we're going to do is we're going to do an example of using the periodic table to determine more complex electron configurations. So let's take a look at the electron configuration for uranium. Here. Uranium's element number 92. So uranium, is it a metal or a non-metal? It's a metal. Actually, uranium is a metal. So in chemical reactions, it would tend to lose electrons or gain electrons? Lose electrons. There's chemical properties of uranium, which would behave like other metals, heavy metals. And there are also radioactive properties. Uranium's radioactive. And so let's take a look at the electron configuration for uranium. It's 92 electrons. So am I going to ask you to draw the orbital energy level? No. In fact, I'm not even going to ask you to do the full electron configuration. I'm just going to say, okay, let's go ahead and use a noble gas. What noble gas would be the closest to uranium? Radon. Radon has 86 electrons. And so we'll start off with radon here, Rn. That has 86. So we got to keep going. So we got 86 electrons. Where does the 87th electron go? Let's take a look at where the 87th electron is. The 87th electron is with francium here. So the 87th electron would be the 7s1. The 88th electron would be 7s2. Where's the 89th electron? 89th electron we have to drop down here. They couldn't make the periodic table wide enough, so they inserted this block here. So we go here, down to here. 89th would be, what is this? These are the F. And so the first F are called the lanthanide series. These fill the 4 F orbitals. So when you look at it, it's hard to see, but they're 4 F orbitals. The actinide series fills the 5 F subshell. And so what we do is we do here, we go 7, it'd be radon 7s1, 7s2, and then we're done with that. So 7s2, fill that. And then we're going to drop down to the 5F. So this will be 5F1, 5F2, 5F3, 5F4. So it looks like it's 7s2, 5F4 in terms of filling order. There, 5F4. No. But can you guys see that? Stay. You see that? Uranium? You get it right? No. Oh, I know what they did. They reversed it, you know. You put it in numerical order. So if we reverse this, put it in reverse meaning, we'll just put it in numerical order. It would be 5F, 4, 7S, 2. But is that right? No. And do you see this? It's actually radon 7S2, 61, 5F3. And so where do we get that? Where you get that is either one, you have to memorize it, or two, you have to use a different periodic table. And looking at the periodic tables here online, there are two types of periodic tables that you can find online. One like this, and then in fact it used to be a lot easier to find the other periodic tables. You look at it, all of them are similar. Do you see? This one's similar. This one's a little different here, but similar. We have different styles of periodic tables here. And so that brings us to this periodic table here. If you look at this periodic table is different than the one I was showing, and most of the ones online. If you look at this periodic table here, we're at radon, which is at 86, and then the 87th is francium. Do you see the 88th? The 88th is radon. And where's the 89th? 89th is here, actinium. And so when we look at this, this would be 7S1, 7S2, 89th would be 61, and then we drop to 90 here, which would be 5F1, 5F2, 5F3. So do you see the different organizational structure of this periodic table versus that one? This periodic table is much easier to read the electron configurations because we just go by the number. We go by the number and then its position here. And so I much prefer this periodic table. Take a look at your periodic table in Chem 4 and see which one it matches with. And then you know how you can do the electron configurations. All right, well, we're out of time here, so we'll stop and then continue next time.